Imagine running a huge program on your computer, but your RAM is nowhere near big enough to hold it all. That's where virtual memory steps in. Virtual memory creates the illusion of a much larger memory space by cleverly using your computer's secondary storage like your hard drive or SSD. This system separates logical memory, what programs see, from physical memory, which is your actual RAM. As a result, you can run large applications and multitask smoothly, even with limited RAM. The operating system, with help from hardware like the Memory Management Unit, MMU, manages this process, mapping virtual addresses to physical locations. This separation is key for modern computing, making it possible to juggle multiple programs and large data sets without constantly running out of memory. One of the most powerful features of virtual memory is demand paging. Instead of loading an entire program into RAM at once, only the parts that are actually needed are brought in as they're accessed. When a program tries to use a part of memory that isn't currently in RAM, a page fault occurs. The operating system then steps in, loads the required page from disk, updates the page table, and resumes execution. This process makes memory use much more efficient and allows for running programs that are larger than the available RAM. However, it also introduces challenges, like delays from page faults and the risk of thrashing if too many faults happen in a short time. Efficient management and understanding of memory access patterns are crucial to keeping everything running smoothly. Virtual memory's efficiency relies heavily on the principle of locality. Temporal locality means that recently accessed data is likely to be used again soon, while spatial locality suggests that data near recently accessed locations will also be needed. These patterns allow the system to predict and preload useful data, reducing page faults and improving performance. The working set, the set of pages actively used at any time, plays a big role. If your RAM can hold the working set, performance soars. Effective access time (EAT) is a key metric, combining the speed of memory access with the cost of handling page faults. Optimizations like increasing RAM, using faster SSDs, and smart prefetching can all help reduce delays and keep your system responsive. Virtual memory brings major benefits. It lets you run programs larger than your RAM, supports better multitasking, and automates memory management and protection. But it's not without challenges. Slow disk access, the risk of thrashing, and the complexity of hardware and algorithms all need to be managed. Design trade-offs come into play. Choosing page size, TLB size, and replacement policies all affect performance and resource use. For example, larger pages mean fewer faults but more wasted space, while smarter replacement policies can improve accuracy but add overhead. Real-world applications like matrix multiplication show that performance improves dramatically if your RAM can hold the working set. Ultimately, understanding these trade-offs helps you design systems that balance speed, efficiency, and reliability.